Is Dr. Kyveryga, and he's going to be speaking to us about statistics. But before we jump into that, I want to just preface this. This topic of ag statistics is something that we in Minka mentioned last year at our annual meeting is something we as advisors wanted to learn more about. A lot of us are in advisory roles with our farmer customers, trying to sort through piles of data to help our customers make the best decisions they can based on data. And with precision ag and all this technology in our industry just continuing to grow, we've got 20 or sometimes 25 years now worth of data to try and sort through. And it's just going to get to be worse, or the data is going to increase as our careers go on. So we need to figure out how to turn this data into knowledge and information for our farmers. So we invited Dr. Kyveryga in this morning from Ankeny, Iowa, uh, to speak to us. Dr. Kyveryga is a senior research scientist for the Iowa Soybean Association. He leads the efforts with that group down there on collecting data and turning it into information for farmers throughout the state of Iowa and well beyond the state of Iowa, based on my experiences working with him. His expertise is in agronomy and statistics and precision ag. He has a PhD in soil science and soil fertility from Iowa State, and he's actually an affiliate assistant professor at the Department of Agronomy at Iowa State. So, with that, I will mute myself and turn it over to you, Peter.
Thank you, Matt, for the nice introduction. Thank you for this invitation in this virtual space. Thanks a lot. Definitely, statistics is a not topic for dinner discussions or even in the bar, but of course, it's everywhere, either in politics, healthcare, business, and so on. Of course, agriculture, it's a big deal. So today, I'll give you some short exposure to basic statistical tools and ideas, especially how we use it, what it means, when to use it, and what it implies. Specifically, I'll describe you the key idea of statistics or any type of science, the difference between target population and sample, and how we draw inference from sample to the target population. And then I'll also give you some hints and ideas for the good experimental design for on-farm trials. I'll also talk about control, like Jay talked before, in slightly different ways. And then the most of time I'll spend showing some of the example of data from Minnesota. That's what Matt shared with me. Those are Afric data, nitrogen trials conducted 2018. And I'll use several tools, the statistical tools, defining the null hypothesis using p-value, t-test, and some other to explain and analyze this data. Although all of these tests are not new for you, sometimes they're often used in some of the presentation by extension and industry. And of course, we'll have a kind of a test or quiz where we will try to define the marriage proposal as a hypothesis testing. So watch for that. And then in the end, I'll show you a couple of cool online resources for studying statistics and using statistics. And one of these sources actually developed by a former banker from Wall Street. He left his job, high-paying job, and developed this Khan Academy source, which really cool and simple for students and us as adults. And finally, I'll show you a couple examples. The most exciting job I do is developing different tools, different apps, so farmers and agronomists can use in summarizing different types of agronomic trials. A little bit about my bio. Matt mentioned that I have a degree in soil science, soil fertility, and statistics from Iowa State. In fact, at Iowa State, I was the last student of late Dr. Alfred Blackmer, and I was working on studying the rates of nitrification of anhydrous ammonia and where actually and serve produce measurable yield response or not. For my job at Iowa Soybean, I do a lot of statistics, both for agronomic and environmental studies. At Iowa State, I engage in different projects, grants, focus on data science, statistics, and precision agriculture. And I also, as a non-academic person, which is unusual, I served twice as a technical editor for the Agronomy Journal, where I helped many scientists and young researchers with statistics and publishing work. And finally, you probably noticed that my accent is not from Iowa nor from Missouri. I'm originally from Ukraine, and if you have any question in Polish, Slovakian, Russian, Belarusian, Ukrainian, please, you can use those languages too. I know that many of you had statistical courses either in high school or in college, and honestly, we all hate it, right? We hate it, we didn't like it, it was just nightmare. Even those people who have PhD, this is not the most fun topic to discuss. So let's discuss, let's see who a statistician is. So one definition, it's a person who answers a question with more questions, right? It's someone who is wrong only 5% of time, and 95% of time he or she is right. It's a person who tries to find the truth in numbers, but she or he is not an accountant. And this is the good one. It's someone that needs an office next to my office. Actually, Matt told me that he needs a statistician just across his hall. Of course, now with pandemic, maybe it's impossible, maybe in his basement, maybe in his neighborhood, but someone who can talk, call anytime he has some questions and problems with data. And the last one, it's more related to academia. Statistician, it's your best friend, but it's a rate-limited person when you're trying to finish a paper report. And that's true, because so many problems, data analysis, we have when trying to finish our project in time. So the key idea of statistics or any sciences is to clearly define what you're trying to measure, what's your target population, and what's your sample. So here on the left, I have this example. Let's assume we have 12 people in the room. Of course, now we have more, and we can only sample every third. So these 4 people which we sample, maybe because we don't have money, we don't have resources, that's going to be our sample. So our inference, our decision will come from the whole population. And this population, this target population, is clearly defined. We have clearly 12 people. Of course, in real life, this target population is not clearly defined. Like here on the right side, let's take Minnesota. And let's assume that I wanna do some agronomic work here, right from MN side to the Iowa border. And I have 6 fields. So my sample size is 6, but my target population is the whole big area. And of course, I don't know how many fields we have in this area, maybe 100,000, 200,000, whatever. But still, it's very important to separate these two definitions, population and sample. Why? Because the goal of statistics is to use your sample, your data, and draw the inferences for the big population. And all statistical tests, they are simple, the ratio of signal to noise, nothing more, no mathematics, no formula. It's a clear, simple way. It's you have to quantify the signal and quantify the noise. And of course, a lot of time we spend trying to quantify the noise. And today I'll show you a couple examples how it's done. So when we talk about population, our target population, our inference space, we have to describe so-called distribution. When we put this data together and plot as a frequency, very often we have a so-called distribution function, something like that. And a lot of time it's a normal distribution like this. It's a bell-shaped curve. Of course, a lot of time it's not normal, which I'll show you later. But these distributions of data usually have 2 characteristics. One is the location or mean. The other is spread or standard deviation. So for example, in this case, on the left, I have distributions of data, my population distributions, which they have the same shape, but have a different location or different mean. So if you go from top to the bottom, the mean goes up. Here on the right, I have a distribution with same mean or same location, but have a different spread. And later I'll show you how we can calculate the spread of this variation. And often here on the bottom, if we have a distribution, again, it's a normal, it's a bell-shaped curve. If it's centered on 0, what we can have, we can clearly define that most of the data in this distribution is coming from plus minus 2 or 3 standard deviation around the mean. That's why a lot of softwares in precision ag are trying to cut the data beyond 3 or 4 standard deviation as an outlier. And that's the basic of this. Of course, if it's normal. Let's go to another idea, how our sample impacts the knowledge about population. So here on the left, I have a normal distribution. Again, this is the bell curve shape. My mean allocation is a red line, and I have a different sample size. Maybe I have 3 fields, 5, 10, or 20. And these dashed red lines, they indicates the plus minus standard deviation from the mean. So you can see that if our sample size is low, a lot of time we don't have much confidence talking about our target population. In this case, you see that our data is going to go beyond of this plus minus standard deviation. As the sample size goes up, the distributions become much tighter, so we are much more confident about the mean. The same about other distributions. For example, this one is skewed. That's what very often we can see in like in income, maybe soil pH, wherever. Even the data which Darcy talked today, a lot of those disease incidents in severity, they are skewed, so they have to transform. This is another way of distribution where actually the data change, but the frequency does not. It's called uniform. It's kind of unique and happened as well. Another way here on the right, you see this irregular distribution where we actually have a bunch of different distribution in one data set. And that's common often with yield maps. But the key idea that as the sample size go up, we have a better knowledge about the mean allocation of our target distribution, the target population. Here's the 3 different distribution. This is sample distribution. They have the same mean, same location, red, blue, and green. But you notice they have a different shape. They have a different spread. So one of them have a low variability, another has a medium, the other has high. So the mean is a technical, relatively simple. We just add it up and divide by number of samples. So in this case, if I have 4 fields or 4 strips, my average is going to be 195. And now I want to explain you what is mean by standard deviation or spread. So I have the same data, same 4 strips. Now I want to estimate the difference between the yield and the mean. So the deviation from the mean is there, 5, minus 10, minus 5, and 10. And of course, these will have a different signs, and then we can square them up. When we square them up, we'll have a square deviation, 25, 100, 25, 100. And then we can estimate our sample variance, which is just simple, the sum of the square deviation divided by the sample size 4 minus 1. The question is why minus 1? Because sample variance sometimes bias. What I mean bias that if you have to, so in large data sets, it can be smaller than it is. So that's why we have to subtract 1. But again, this is the sample variance. Of course, dealing with the square acre, square bushel is nonsense. Usually what we do, we take a square root and then we have a so-called standard deviation, which is 9.1. So again, the mean is 195 bushel, the variance 83, and standard deviation is 9.1. So these are key characteristics of these sample distributions. Again, the more data we have, the better chance that we get more close to our population mean and population variance standard deviation. For example, this is another idea. I have 3 fields, 1, 2, and 3, painted in different colors. So you see that when the sample size is small, maybe around 10 or 20, it bounces back and forth. But sometimes when the sample size becomes maybe 100, we are close to our target, our population mean. Everything it converges to the one. For the standard deviation, it's the same. So again, the same 3 fields. If I calculate this sample standard deviation, you notice that maybe sometimes around 70 samples, 70 fields, or 70 observation, my sample deviation becomes population deviation. It becomes the constant, the one number, which is good. Another way what usually people do, and we have to be careful, we express as a standard deviation for the mean or standard error for the mean. So in this case, we divide standard deviation by sample mean squared. So if we start with low sample, maybe from 1 to 10, you notice that the standard error for the mean is large. But then as we get closer to 30, 40, and 50, it goes up. So again, this is just a different way to express our sample noise and sample variance as a standard error of mean. But again, the sample size is a big deal. It gets us closer to the population, to our target. And now I'm going to talk about the data. So again, thanks, Matt, for sharing this data. These are on-farm trials, nitrogen trials from Minnesota. This is the AFRIC study, AFRIC program conducted in 2018. I'm going to just use 1 year. These are green dots. They are spread across the state. The design is simple. They have only 3 treatments. One is MRTM. It's a maximum rate to nitrogen rate, which farmers use based on a website developed by different states. And then the other treatment, the second treatment, is MRTN minus 30 pounds. And the last one is MRTN plus 30 pounds. So the goal of this is to validate MRTN, or in my sense, we're trying to quantify the agronomic and economic risk of over applying or applying below the MRTN. So again, this is an example of these studies. So most of the data sets I'll show about this. Of course, me as a data scientist, a lot of time we're developing these online interactive tools. And this is what we started developing last spring. And again, this is data from AFRIC study 2018. And one of the goals of this tool is to have a different type of analysis and summaries in one place, just not to play with PDF, SPAR and stuff like that. But the way I like to look at different data is to look at the trend. So here's I have 3 treatments, black dots. I have a trend, these blue lines. I have an average MRTN rate. Sometimes is exactly on the center, sometimes it's not. But what I'm looking for here, I'm looking for trends. Sometimes the yield goes up, sometimes stays the same, sometimes it goes down. Of course, we don't need to confuse these for yield response curves, which is usually done by university folks or researchers, where they have ability to apply a wide range of rates, especially low rates where we have a large yield losses. But again, this is the way I like to look at the data. So now I want to look at the sample distribution of corn yield for 2 different rotations. And this is 2018. So these are sample distributions. You see that one is for corn after corn, which is red. The other is for corn after soybean, the blue. And you notice that they're more or less normal, right? They have this shape type curve. You notice that these solid lines, those are means, and the dashed lines, those are medians. You notice that the mean for the corn after soybean is larger than corn after corn, which makes sense, right? We have some kind of yield drag. The medians, unlike average or means, it splits distribution into 2 equal halves. So the half distribution is below median, and the other half is above median. So you notice that here, the medians are slightly higher than means, which means they're a little bit skewed, and the standard deviation is the same. So the noise in this distribution is the same, which is a good sign. But again, these are just corn after corn, corn after soybean, without considering treatments. So the question is, why? What's the sort of this variation in this on-farm trial or any type of field experiments? There are 2 different sorts of variation. One is biological or agronomic, and the other is technical. The agronomic variation is because of either treatment, spatial variability, temporal variability, plant growth, and all kind of potential interaction. The technical variation, it's a noise. This noise comes from instruments, from our planter, from our tillage, sprayers, accuracy, calibration, even operator. For example, if the yield, if the son harvests yield in the morning and then his grandpa comes harvesting afternoon, again, it could be a big effect in speed, style, and so on. So the technical variation, that's what we try to reduce. And then we try to expand or better quantify biological agronomic variation, which is a signal. Let's have an example of small plot versus on-farm trials. And a lot of time when I work with farmers or agronomists, they ask, what's the main difference between two? So this is the example from one of the book chapters we published for NRCS, where we try to explain the key difference between small plot trials or experiments, which usually done by university scientists, and on-farm trials, which usually you and your customer do. So this is corn, this is nitrogen trial. You see these strips, and this is small plot trial. So usually the size is different. The small plot trials, they use about maybe half football field size, when on farm trials, they can range from 20, 40, even 80 acres. You notice that there are some streaks here, and those are drainage. So the goal of small plot trials is to position in such a way that you capture the uniform area, while for on-farm trials, a lot of time you capture they capture the wide range of variability in soil and other properties. That's the key difference between two. So now I'm going to talk about the basic of field experimentation, and one of them I wanna throw this joke. So we have a family of statistician and his wife. They have a infant twin sons, and for baptizing, they only brought one son to the church. And the priest asked, where's the second baby? And the happy father replied, well, I left him at home. So he left the second baby at home as a control. And now I'm going to explain the difference, what Jay talked about control in nitrification versus statistical control. And this is the joke, but the truth is that a lot of time when farmers talk to me, they say, Peter, you know, I harvested my field and I saw this big yield response to this product or treatment, 10 bushels. How did you see it? I saw my yield response. Did you have control? No, I did not. So again, this is not a joke. So the most important is to have a control, which would allow to compare what you do with something you want to measure. Another importance of a good experimental design is to have treatment replications. And again, replications are needed in order to quantify the noise and variation. And later, which I'll show you, conduct statistical analysis. Blocking. Blocking, it's another term you probably will hear. Blocking, it's a more statistical things which allows to reduce variation and increase precision by dividing your experiments into different sub experiments. So essentially, in one experiment, you have several of those, and that will help you maybe reduce the effect of differences in drainage, elevation, texture, and so on. Another important feature of good experimentation is treatment randomization. It's used to avoid potential bias, which may arise, for example, if the same treatment exactly hit the tillage passes, or the same treatment hit exactly the crop residue passes, or something else. So the randomization is critical, especially to avoid potential bias. But all of these are important pieces, especially local control. Now, how we have to, what's this best stewardship for field experiments and farm trials? One, I mentioned we have to control unimportant noise and variation. Another, our treatments should be precise and have a good representation. So here's an example. Again, I have this example of this target distribution or target population, this bell-shaped curve. I have only two treatments, B and A. So the blue is B, the green is A. You notice that all of these treatments are located only in one side of my target distribution, only on the left. We only cover the low numbers, but the rest of distribution is empty. So it has a poor representation, but they are precise since you notice that the difference between treatment is very consistent. Here in the middle, my design is not precise, but representative. Since again, I position my treatments for the whole population distribution, but you notice that the yield difference is not consistent. So I have to have a replication. Here on the right, my design is precise and representative. I have a 3 replication in each block, and you notice that the difference is consistent in this block. It's very small here, larger in block 2, and the highest in block 3. So again, keep in mind that our experimental design should be precise and have a good representation to what we measure. Now I'm going back to the treatment. These are a sample distribution for our treatments. On the left is corn after soybean with 3 treatments, MRTN orange, MRTN minus 30 green, and MRTN plus 30 blue. And on the right, it's a corn after corn. You notice that corn after soybean, the sample distributions are a little bit skewed to the right. These dashed lines, those are averages. And you notice that the difference between 3 treatments across all of these trials is not big relatively to the variation in the data. But again, that's another way which is very useful to look at the data. And especially with all this big data which Matt mentioned, that's very important. Now, what I told you was just an introduction, kind of the basic. Now it's kind of the real stuff. One of the important things in statistics is clearly define your hypothesis and hypothesis testing. So to give you some introduction, let's consider this marriage proposal. So this fellow, he is proposing a marriage to a woman, and it turns out she's a statistician. So in her mind, she has 2 choices. One, she would say, I failed to reject the null hypothesis here on the left. You notice it's triple negative. And here on the right, she said, I reject the null hypothesis. So think about this, and we'll come back again. He is proposing her, she replied, and he doesn't have a clue what it means. So I assume he probably had some statistical courses, or maybe he slept or looked at his cell phone. So he is in big trouble. So let's clearly define what doesn't mean hypothesis testing in agronomic studies. And we'll go back to this again. So the null hypothesis, that's critical. The null hypothesis, that's the things when we look at the hypothesis testing, it's all about population mean, it's all about population stuff. So in this case, for example, we claim that the yield at MRTN and yield at MRTN plus 30 is the same. Or another way we can say that the difference between yield MRTN minus MRTN plus 30 equals 0 or nil. That's why it's called null hypothesis. The alternative hypothesis tells the opposite. It tells that the yield at MRTN and MRTN plus 30 are not the same. They're not the same. They're different. The yield difference is not nil, is not 0. So again, these are example how you set up this the null hypothesis. Of course, let's go back to the marriage proposal. So what is the null hypothesis for the marriage proposal? Any ideas? I assume it's a no marriage, right? In her mind, it's no marriage. And the alternative hypothesis is marriage. So when she said, I reject the null hypothesis, what did she say? Of course, she said yes. But again, that's confusing part in statistics. So let's look at another way. Of course, for the null hypothesis, we can have two situations. One, when our null hypothesis is true, or when our null hypothesis is false. And then we may have a 4 different decisions. In one, when we accept our hypothesis when it's true, so we make a correct decision, or we reject. And that's called false positive, because when there is no results, but we claim as a truth, that's called false positive or type 1 error. And often it's defined by so-called alpha or significance level. And usually scientists assign 1%, 5%. I noticed Darcy used 5%. We often here use 10%. So again, you have to see this because it's a maximum amount of false positive you can accept. When the null hypothesis actually falls, you can create so-called false negative error or type 2 errors, which is also important in many cases. So a lot of time, the null hypothesis is only focused on controlling false positives. And the ways it's measured, how strong is whether your hypothesis is true or not, it's measured by so-called p-value. And to describe you what is p-value, I have this example from Iowa. And so these are fungicide trials. They're conducted in Iowa. There are only 2 treatments. This is fungicide versus untreated control, blue and red. So to describe you what p-value means, let's do this exercise. I'll tell my computer to forget what these treatments are. So my computer randomly sample a pair of these strips, estimate yield difference, put in this distribution here on the bottom, and does it hundreds, thousands of times. So essentially, it developed this distribution of random noise. And now we look at the distribution of random noise, the distribution of null hypothesis, and see how our observed yield difference, which is 2.3, is common in this distribution of random noise. If it's too common, which means that we don't have any evidence to reject the null hypothesis. In our case, you notice that we have about 5% of data about 2.3 and 5% of data below minus 2.3. So in our case, the p-value is about 0.10. So if our significance level is 5%, then we would definitely say that it's not significant. If it's 10%, then we would claim that maybe there is some evidence that our null hypothesis is not correct, so we can claim that there is a true effect. So again, the smaller the p-value, the stronger the evidence that the null hypothesis is not correct, and we can reject it. So let's do another example. So let's take one of the trial, so to get you some understanding what it means. So here I have a trial. It's one of the trial. Again, here is the MRTN, right? Here's MRTN minus 30, and here's MRTN plus 30. Let's look only at the 2 treatments. 1,6 MRTN and MRTN plus 30. So I put these side by side by pairs. These are yields. I can estimate yield difference by these pairs, and then I can estimate the standard deviation for these pairs, which is 2. And notice that the yield difference is 2. So sorry, the mean yield difference is 2. And then I can estimate the standard deviation. The standard deviation for this is 3.4. So the standard error of the mean is 3.4. And then I can conduct my test. And again, the test is relatively simple idea. It's a signal to noise ratio. So I have a signal which is 2 yield difference. My noise is 3.4. So if I take 2, subtract 0, and 0 it's symbolic because the null hypothesis includes 0. 2 divided by 3.4, my ratio, my statistic is 0.57. It's pretty low, right? And again, the t distribution, it's the same like a normal distribution. It's only have a slightly higher tails. But my distribution, my distribution of random noise is defined by this t value, which is 3.7. So now I'm looking, what's the chance that 3.7 is going to be higher than my observed t value, 0.557? And in fact, it's 0.62, 62%, which means that if we use a cutoff of 0.10 p-value, the difference in this treatment is not significant. So again, this is example how we can use p-value, how scientists use p-value to use this statistical testing, especially this so-called pair t-test. Of course, a lot of time, statistical software would give this automatically, and usually people classify these p-values by the evidence to reject of null hypothesis. If it's higher than 10%, there is no evidence. If it's between 10 and 500, it's a weak evidence. If it's between 500 and 100, or maybe lower, there is a strong evidence. And usually what people do, they would put these stars in some of the table or some of the charts. The problem is with this that a lot of time the software does it automatically and people just overuse it and use it. So a couple years ago, the Statistical Association of America put a statement which says that scientific conclusions should not be based only on whether p-value passes the specific threshold. Again, because there is more to p-value. It's important, but you have to have more evidence, more showing more data. I'll show you how it's done. So remember that the p-value is only one tool. It's based on hypothesis testing, and a lot of times scientists would abuse it since software does it automatically for different reasons. Now I want to go to trying to compare different groups, especially 3 different groups. We just discussed 2 different groups. I want to mention this fellow, this brilliant scientist, Ronald Fisher, Sir Ronald Fisher. He is the founder of X statistic. In fact, the whole statistic came from agriculture. That's very important to remember. He was a British statistician, mathematician, and geneticist. He was assigned to work at the Rosenstedt experimental station in UK between 1919 and 1933. And he got a lot of data. Those are long-term experiments with wheat, fertilizer, manure. And using this agricultural data, he developed very brilliant ideas and tools and methods which we're still using until now, like analysis of variance, experimental design methods, and so on. The interesting stuff about Ronald Fisher, he came to and visited Ames, Iowa State. He was offered a job and he declined. And the reason he declined was that his wife, she didn't like the hot and humid summer in Iowa. And of course, the joke was that we're glad we didn't invite him during winter. But again, remember that Fisher, it's a big name, and a lot of tests like F-test, it's because of his name. So let's go to the 3 treatments comparison. I showed you these two. Let's put another one. So this is the same trial, same design. Now I have a 3rd treatment, which is MRTN minus 30. And you notice that it has the larger variability. So again, the null hypothesis is no different between treatment, and the true hypothesis is there is treatment. And again, I can do the same. This is the called analysis variances. And the basic idea of this, again, you're trying to classify or sort variability by different parts. In this case, we sort variability by treatment, replication, and residual. So the null hypothesis here that all means are the same, just use one means, and the signal in this case is 25. And the statistical F-test is 25 divided by 31, which is, again, it's relatively small and p-value is big. And in this case, there is no evidence to prove that our hypothesis is incorrect, so the treatment differences are the same. A lot of questions people would ask about least significant difference idea. And here's the example to calculate least significant difference. It's a threshold which would indicate whether the difference is significant or not. And I noticed that in Darcy's presentation, she had some treatments labeled by letters. In our case, LSD here is 9.5. The yield differences are smaller, they're not higher than 9.6. And in this case, we cannot claim they are different. The trick is that we cannot calculate LSD if its overall F-test is not significant. That's why it's called protected F-test, and a lot of time a scientist would abuse this as well because computer does it automatically. Another way to look at this data is to look at not yield, but look at yield loss from reduced rate and increased rate. like in this case. And what is interesting about this data, that when I look at the yield loss, here's the yield loss on the left, yield gain on the right. When I look at this data, it looks like there is a nice trend. The yield loss from MRTM is higher when the organic matter is lower. In fact, we saw the same in Iowa. So again, it's lower, especially for Southeast Minnesota and Southwest Minnesota. As organic matter gets lower, the yield loss from reduced nitrogen is larger. And again, this is another idea of using a so-called regression analysis, which allows to connect independent variable, which is organic matter and yield loss. And then the most useful part actually is, instead of using p-value, I would recommend to use so-called confidence interval. And this is example of confidence interval. And again, this is the yield loss from reduced N. This is the yield gain from additional N. This is 90% confidence interval. It's a range. This range indicates how often you would get your population mean fall in this range. So in this case, 90%, which tells that 90%, I'm confident 90% of time, my range would have this mean. And in this case, since here it includes zeros, I would claim that this is not statistically different. In this case, it is. I'll show you a couple examples of this confidence interval in this tool. Again, this is effort data. Noted that everything expresses confidence interval for both individual fields and population means. If this interval doesn't cross zero, they're significant. This tool which we developed, a prototype, it automatically allows to select different probability values, 80%, 90%, 95%, and so on. It tells how many of these trials are significant on the fly. Plus, you can do economic analysis where you can plug different prices for the grain and treatments, and it estimates the chance to exceed the break-even cost, the low operating cost, and does a lot of economic analysis on the fly. And finally, I want to show you these cool sources to learn statistics or maybe help your kids or grandkids. One of them is Khan Academy. I mentioned this fellow who left Wall Street and established this nonprofit company. This is really cool. You can Google, it's free. Some other, they usually have maybe $5 or $10 fee, but again, they're really focused on adults like us. And these are some of the tools we developed in Iowa. You can go to our website. These are for farm trials, imagery, soybean calculator, soil health, a lot of interactive apps, online tools. And this is one of them we developed at Iowa State University, which has almost 2,000 different farm trials, and you can look at those and see how it works. So that's all what I have.
Great. Thank you very much, Peter. Really appreciate that presentation. It was very interesting and certainly not something that we get in the course of a normal agronomy update, I would say. That's kind of an experience to learn more about statistics. Are there any questions from the group? I don't see anything in the chat session, but you can certainly unmute yourself and ask Peter the question directly. About 5 minutes here. While we wait for questions to come in, Peter, I'm just curious, how many years have you been doing this work in Iowa, and roughly how many trials have you analyzed over your career?
Yeah, good question. The question is how many years I've been doing this. I've been with Iowa State Association for 14 years. So that's a lot of time, more than 10 years. We have a historical data sets. The tool I showed you, it's called ISOFAST. It has probably about between 2,000 and 3,000 trials on farm trials, replicated farm trials with different products, technologies, and practices in both corn and soybean. Yep, Dr. Goose.
Now, back when I took statistics literally during the Carter administration, we were taught that for an agronomic trial, say a variety trial or a fertilizer trial, that a coefficient of variability, which is 100 times the standard deviation divided by the mean, say 15% was pretty good. And a coefficient of variability of 10% was amazing. And that old lesson has stuck in my mind. And I look at the claims of, let's be kind and say, non-traditional inputs for farmers. And I look at one and they say gives a 9 bushel per acre yield increase in corn. And I'm thinking, man, if they did their farm trials at 200 bushels per acre, 9 bushels per acre is less than a 5% yield increase. Can you really pull a 5% yield increase out of the noise in regular agronomic trials, let alone farm strip trials? Can you really pull a 5% difference out of that?
Good question. So you kind of rephrasing your question is about the sensitivity of on-farm experiments, especially to measure in the small yield responses, small yield differences. Definitely, that's the important topic. And here we have to consider two different parts. One is whether you're looking for sensitivity for population level, for the regional level, or you're considering sensitivity for individual location. And that's sometimes very confusing, because for population level, if you have enough observation, enough location, right, and your treatments are consistent, you may have the sensitivity to detect these 5 bushels. A lot of time for individual locations, you don't have it. But your decision, your agronomic decision, which is going to be not this year, but next year, you have to consider both. And that's why the modern trend in statistics, and especially in predictive analytics, is to try and to not only tell about the inference, statistical inference, but also tell it what really explains this yield difference, what really can reduce, like in case of the nitrification inhibitor, or like from my studies from Iowa State was nitrification rates in anhydrous ammonia, we learned that pH can help to explain some of this variability, and that's very important. So again, sensitivity, it's important, and it's also different for field experiments and of course the lab studies, right? The field experiments are much more noisier in some sense. Although we compared side by side small plot trials with universities and our trials for fungicide, and we noticed that the effect was the same, but the noise in on-farm trials was the smaller. And was the smaller because the size of the fields, the size of the strips is much larger, so it's much more reliable estimates of yield.
Well, I don't have a problem with a low-cost input like a seed treatment. If a seed treatment is less for corn is $10 an acre, if there is a proven mode of action that it affects this disease or this insect, you may not ever be able to pick up that yield increase statistically, but there's a mode of action behind it. But sometimes these snake oil products, they'll just say, put it on and get, I got this bar graph and I got this bar graph. And so I'm always skeptical when with those sorts of trials, I guess.
Yeah, good point. One of the strategies we started talking to farmers, not just about statistical inference, but what's your predictive interval? And predictive interval, it's an interval in new situation, which kind of, it's wide, right? But it tells you how often your treatment is going to be negative or positive. And that's not only after the fact, but you would add more noise, artificially more noise, because again, your decision is going to be next year. And that's called predictive analytics. That's a lot of people trying to predict. So inference after the past and predictions slightly different, but you have to have a good sense of sensitivity from the past.
Thanks for the question. We've got just time for one more question here from Toshi at the University of Minnesota. The question is, what variable do you see that explains the variability of corn yield based on your experiences there? It's in the chat session if you want to take a look at it, Peter.
Yep.
And then question is, do you also conduct spatial analysis? So that'd be GIS type analysis as well.
Yeah, we do conduct spatial analysis in some locations. Unfortunately, of course, there are two separate questions. One is question, what explains spatial variability in yield? It's important, but a lot of time it's not really relevant since we are looking for variability in response. We can quantify variability in corn, spatial variability, and it can be elevation, topography, soil types. But what's more important, it's yield response, yield difference, our signal, right? I mentioned the signal, and the signal is measured by response difference. And a lot of time we cannot. Sometimes we do, but a lot of time we cannot really, because temporal variability is large or we have too much noise.
Great. Peter, thanks again for your time with us this morning, talking to the group. We really appreciate that. As we
Welcome.
shift gears here, one thing that is to close out this segment of our talks this morning is that I know that almost 98% of the population now lives in non-ag areas. So we as people working in agriculture have to be able to communicate with our decision makers who live in St. Paul and in Des Moines and in Lincoln and in state capitals where policies are made. So data is one of the ways that we can do that in our jobs as consultants, to communicate what we're seeing and also to help our farmer customers maximize economics and yield and the things that are important to them. So right now I'm going to turn it over to Dan Nielsen for some closing remarks. Dan?
All right. Good to see everybody. Like to thank the speakers here this morning. Peter, great job there. Darcy and Jay, definitely appreciate your time. And our group definitely values all the input. And I'm sure we all have a good takeaway from this. So second of all, I'd like to thank the Education Committee. The committee this year, we had Jim Gill, Matt Weavers, Stephen Nelson, Wayne McClintock, and Mike Point and myself. So we are not used to doing it like this, and hopefully we don't have to in the future, but I think it worked real well for today's purposes on that. Next step here, I think Lance is going to put a QR code up on this break here now. So if you guys do have the CCA, you can just take it and scan it on your phone. If you don't have that, you can sure check in with us and we can talk about and put your name on a list and send them in too. So, well, with that, we got our annual meeting here. We're going to start like in 5 minutes. So I guess 5 minutes from now, we'll start that up and we'll go from there. Thanks, everybody.